Hello, yes.
So is everybody watching can everybody see the PowerPoint?
Yes, we see.
Okay, shall we start then? Okay, hi, hello everyone. Um, my name is Jairo Balcácer. I will present this webinar. Basically, it's talking about gas lift and ESP. On the gas lift, we will, as it is in the agenda, we will talk about gas lift optimization, troubleshooting in mainly three areas. Inlet problems, we will define that, outlet problems, and downhole problems. And something, just a word on tuning the well. And we will see a gas lift design and example. Basically, is a gas lift ratio optimization. Is how much gas we have and how much we can inject in order to get the optimum performance. On the ESP, we will start something on the non-standard conditions. Basically, we will define what are the standard conditions for the ESP, and so non-standard conditions like production viscous fluids, low rate pumps, and gas wells, and some solutions, production of abrasive solids, and ESP design example. With this, we will start then with the gas lift optimization. First, we need to define what is the optimum production by the gas lift. It's basically is a stable rate, which is attained by a specific gas injection rate, leading to the a sustained production for a long time. It means we can have different volumes of gas, but maybe if they are not optimum, you will not get this, a sustained production for a long time. So that's defined as optimum. Uh, uh, Basically, one of the issues or one of the facts is that the optimum amount of gas normally we have to define by well test, you know. So regardless of the volume that we have, it's better to go with well test and define the optimum conditions. We will see that. Another way of optimize the gas lift injection is attain what is called the optimum profitability. This is obtained by using the gas lift performance curve, which is, we can get this from Prosper. So the method to get this optimum profitability is selecting 4 points on the curve performance, that the one we get from Prosper. Draw tangents to each point. We will see that. Generate the slopes, and the slopes are plotted as a against gas injection rate. So the high gas injection rates in general do not produce oil rates that longer than the optimum gas injection rate. Too much or too little injection gas will result in less than maximum production. So we are here, the target is get the maximum production. That's the target. So here we have the red curve. This is the plot of gas lift performance curve. So with that one, and that's the one we get from Prosper, we run some tests, or where we get some points like A, B, C, D, and for each point we come, and at that tangent we get the slope. So with this slope, we will here in the plot to the right, we have a plot, a slot versus the gas injection. So it means for each test A, B, C, or D, we got the slope again, and with this we will create this plot, which is the plot of slope against gas injected. So here we have the M definition, which is the slope is the amount the gas lift cost in dollars per million of standard cubic feet. The oil cut, which is FO, and P is the profit. It means how many dollars we get from each barrel. So with this we get the M, and with that M we get this curve. So then with this, in any time we need to having the slope defined from the gas lift performance curve and the value of the gas lift cost, the oil cut, and the profit per barrel, the M value, which is right here, this M, is defined, and with the curve, the optimum gas injection is defined. So it means any point that we need to get right here in this curve, we come and use that slope here in the curve, and we get the optimum gas injection. Again, the recommendation is validate those values, those numbers, with well test. Injecting above or below this value will not get the higher liquid production, the optimum liquid production. And of course, another way to get the optimum gas lift is by well test. So it means we run a test, and we get the number of gas injections, and we get for that specific, we get a specific oil production. So we are plotting here gas injection and oil production for different tests. So right here we have 3 or 4 tests done run in that case, and in that way we get the curve, this which is the performance curve. So this is again by well test. So this is a recommended procedure. You can get, starting from a low gas injection. The idea is started with the low gas injection, and increasing and getting the production. Of course, you need to stabilize the production at least 24 hours per point. So in that way, you are running a test, getting a volume, getting the volume in injection, and for that injection, you are getting an oil production. And then you leave this for 24 hours and continue, running, injecting a different volume. In this way, you get the optimum volume. So you can get, you can plot this, and this is for it takes time, is not for everybody, every well, running a test, but this is something that it will take 1 week, at least for the best productions, for the best well producers in the field. We can do that, and you optimize in this is an optimization process. And so gas lift troubleshooting. So it means whenever we have problems in the field, you know what to do. You know, field techniques, those are field techniques. One of the main issues in the gas lift is called the point of injection. You know, the technique more suitable for a particular well, of course, should be carefully defined to avoid unnecessary expenses. In case, you know, we have to work first on the surface, you know, um, either the gas injection or the producing lines. We have to work on this before going downhole. Of course, you know, one intervention is costly, and sometimes it requires even the rig, because we are dealing probably with the some problem in the leaks or something like that. The most common test just to get the point of injection is communication test. One communication test defines the holes, any damage check valve and CT valves, leaking completion packers, or at the end, any annulus tubing communication. Then the troubleshooting steps, there are three main areas. Inlet, which is right here. On this schematic, we have the downhole, you know, the compressor, and the outlet. The outlet is from the wellhead down to the separator. That's the outlet. The inlet is from the compressor down to the wellhead, surface, and downhole. Again, the idea is troubleshoot should start at the surface to avoid expense risk, of course, to investigate any downhole problem. So first, analyze starting from surface gauges should be calibrated, you know, because sometimes you get some problems and wrong readings, and it is related to calibration. Inlet problems, excessive gas, casing pressure or injection, tubing or collar leak, washout lead valve, you know. Those are some of the inlet problems. Shock sizing, of course, if the shock, the size of the shock is wrong, we get either too much or too little, or, you know, or deficient gas. Faulty gauges, of course, as I mentioned, just to read the wellhead casing or tubing pressures. Another problem is high casing pressure, is gas injection volume due to partially plugged valves. You know, that in that case, those are sources of the potential high casing pressure. Flowing temperature, higher tubing pressure, a restriction in the tubing. Those are inlet pressures. Another one problem, low gas usage. You know, confirm gas volume. We have to we have to confirm the gas volume injection meter is currently, you know, working. Verify the operation temperature of the gas lead valve. Why the temperature? Remember that the gas lead are tested in the shop at the defined temperature, operating temperature. And if the temperature is different, of course, we are talking about different conditions. So we are not, I mean, the gas injection is not working properly at the optimum condition. Also the test injection of the flow shock. Then the outlet problems, again, is from the wellhead to the separator. High back pressure is an indicator of problem with the outlet, you know. Restriction through the choke, debris, or maybe some solids for instance, if it's winter time, maybe we get some paraffin or wax deposits. So those are causing high back pressure. Paraffin or scale flow lines, when we have flow lines 90-degree turns or avos, those are not recommended. You know, the stray, the more stray we have the system flow lines and everything is the better. Separator operating pressure should be, this pressure should be maintained as low as possible. Critical in gas lift wells, of course, you know, the lower this separator pressure, the less is the back pressure, or you know, required to produce the well. I mean, you are optimizing, you know, the lower the separator pressure, the more chances to get optimum or higher flow rates. And valve restriction, of course, you know, all the valves should be fully open and properly designed. Smashed flow lines or road crossing places, those should be checked and you know, remediated in case there's a problem. Downhole problems, we have more difficult, those are more difficult to identify. Only approach is to interpret the information and find out. Blowing gas dry is one of the, basically you are just injecting gas and producing gas, which is basically you are not doing anything. And some casing pressure exceeding the well-designed operation pressure, tubing communication, a leak point, you know, we have to verify that, you know, where is the actual, you know, fluid level, you know, that's with the echo-meter or survey. Verify the inflow from formation. If there is, you know, maybe we are having a well that for some reason either is the perforations are clogged, or the influx from the reservoir is changing or decreased. So we have to verify this. Also, we have to check that RP valves are operating properly. Then the issue is below. Some downhole probe frozen choke. Another problem, well flowing in heads. So it means too much or too little gas injection. The pore size of the valves, you know, are not properly designed. The temperature, especially when we don't have the data, proper data to design, then maybe the flow rate we are expecting is lower than the actual flow rate. So it means in this case, the flow rate is, the fluid is changing the temperature of operating temperature. So this create cooling effect on the valves. And also I mean, the high flow is heating or increasing the temperature. So the idea is to stop and leave the valves will open again when they cool off. And so downhole pressure, another one is the well will not unload due to the fluid column is heavier than available lift pressure. The wellhead back pressure is too high. The valve is staying open due to the sediments or salts or other deposits. And holding the tubing, we mentioned that also. But the valve is staying open. The valve spacing is too wide. You know, if a high nitrogen pressure is nearby, we can use or the well or use nitrogen in order to solve the issue. I mean, to unload the well. Then if the problem is still in the well, we have not solved the problem. We have to respace the valves. Pack off gas leaf is required, or shoot the tubing to get a new point of injection. Tuning the well is unloading the well requires more gas, of course, than volume injection at the beginning, than when the well is in operation. So it means it requires a higher volume of gas. Often the input gas volume can be reduced once the point of injection has been reached. So it means the idea that's the normal. The recommendation is to start the well on a small input choke like 864s, then increase by 164 increments until the maximum flow rate is achieved. So allowing for each increment, 24 hours after, the chain, and before I get in another chain. One way to troubleshoot is just run a log, temperature log, and in that way we can check if there is a problem with the holes, friction, or whatever. So we will go and now to check, determine there are two examples, determine the optimum gas leak ratio given the condition unlimited amount of gas is available, or a given amount of gas is limited. We will see those. I will load the example. Here we have the example. The idea then is determine the optimum gas leak ratio given any conditions. So once we define the optimum gas leak ratio, we need to calculate the required injection gas leak. By using this formula, gas leak ratio injection is the optimum minus the formation, gas leak coming from the formation. So the required gas injection to the well is the gas leak injection times the rate. That's the expected production, expected gas leak ratio injection. Now, if only a limited amount of gas is available, there is a well potential gas leak ratio is gas leaks coming from the formation plus the ratio of gas Q available over Q. So QG is the gas leak injection rate available to the well. So we have an example right here, and is everybody listening? No problem.
Yes, of course.
Okay, wait a minute. Okay, the example, we have a well with mid perforations at 5,200 feet, oil gravity 26, which is equivalent to this 0.9. Here I have the conversion from basically based on the oil gravity, and based on that we have the gradient of that fluid, and so in PSI, and we have a gas leak ratio of 300 standard cubic feet over Stockton barrel. So from the IPL of the well, as we know, this expression Q is this is basically the equation to get the the ratio between the downhole flowing pressure and the reservoir pressure, and once we get the Q maximum rate. So with this information right here, we have The Q maximum is 1,500. Average reservoir pressure is 2,000 psi. The tubing ID is 2.5 inch, and the tubing OD, sorry, the 2.5 is the OD. The ID 2.259. The packer is set at 5,000 feet, and the water pressure is 200 psi. So as we see, basically the packer is set 200 feet above the mid perforations. So the idea is to know what is the maximum expected oil rate from the well with continuous gas lift. If we have those two situations, one, the A is a limited amount of gas available. You know, sometimes we have some fields, we have this let's say privilege having, you know, whatever we need. And in the case we have only 1 million standard cubic feet available. So the maximum oil rate production is expected with gas injection, of course, above the packer. Assuming pressure loss due to the friction below the injection point are negligible. The inflow performance curve for the gas injection point inside the tubing, based on this equation that we saw before, and the calculation of considering here the setting of the packer and the setting of the valves and the gradient of the fluid, which is the one we right here we have. So based with this equation, here the gradient again is the one we calculated back here, and this is the setting depth of the bulk, and this is the total depth. Have those optimum gas lift ratio sheet. We have those three. This is any values and the gas lift ratio, and in order to get the production tubing, you know. In this case, in this right here, we have is for the production, we have the gas lift ratio, which is calculated as before, you know. But with this for the same production, we need to get this with the Hagedorn and Brown correlation, basically, or in the Prosper, we get this and we get the production tubing, which is is a correlation downhole surface. With this, we have right here, we build this table, production, inflow pressure, and outflow pressure. The plot shows the operating point, you know, here for this rate. We have the pressure, which is basically in this system analysis right here. This is the blue curve is the production and the inflow pressure, and the outflow is of course the production. And so the intersection is basically what is showing right here the intersection is 632 barrels per day. So, and the injection gas lift, this is the optimum gas lift calculated by interpolation based on this is this amount 3072. This is the gas lift ratio, so a surface. So the injection gas lift in this case is this, which is the difference between 3072 and the gas lift ratio right here, the data given, which is from the well. So the required gas injection to the well is this. It basically is the injection gas lift times the ideal rate, which is the given by from the intersection right here. So this is again, this is for the case of unlimited amount of gas available. Now we go and we need to find out which is the required gas injection. But in the case of having only 1 million standard cubic feet per day, then in that case, the gas lift ratio is the gas lift coming from the formation plus the gas injection which is available. In this case, is 1 million divided by the rate. So with this, we got this table. We will get the same three numbers, 400, 600, 800 as a rate. And with that one, we calculate, again, with this equation, we calculate the gas lift ratio. So again, with that one, this information, and with the data sheet, the Hager-Brown correlation, it's a data sheet I have. I can share if in case somebody needs this sheet to calculate this. With that one, you for each rate, you calculate the tubing pressure here. And in this case, we have in this case, the rate is 620 and the tubing pressure is 702. So we see, it's of course, it's a lot of details in this, but we see that in this case we have 320 barrels as an idea. We have here in the previous one, when we have unlimited amount 632 and we 698 psi as a tubing wellhead pressure. In this case is 620. I mean, the difference is really small in those two cases. So the recommendation then is basically that increasing the gas injection from 1 million and there is no extra gain, there is no really different, but you are saving a lot of money not injecting and compressing to higher rates and wasting money with really when the injection or the optimum production is not really a big difference. So now we continue with the presentation, and we will go back here to we will go now with the ESP system.